Hi, today we'll be talking about IMU path detection as the course project. This deals with localization and path detection. So, what are the prior works of localization? So, GPS is one of the widely used methods to localize and to determine the path. The pros are it can be efficiently tracked outdoors and there are a lot of APIs available. But the cons are in indoor locations, GPS loses signal and it also could be huge drain in the energy. So we need to find out what are the ways to localize within a building. So one of the method could be using predetermined resources like routers or Bluetooth devices, and then check their signal strength and then triangulate them to find out where we are actually situated. And but this suffers with the problem is we need a huge setup cost and we need to crowdsource the data in order to determine which location corresponds to what signal strength. So this brings us to IMU data reckoning, which doesn't need any external data, which requires embedded sensors and it requires no setup. So it's very portable. So what are the inputs and outputs of the IMU data reckoning? It's accelerometer and gyroscope data, and it gives us the orientation of the device and the path of the device. So what are the three important steps of the IMU data reckoning? It's step counter, walking direction detection, and the step length. The step counter tells us when we are taking the steps, and if we are moving or not. The walking direction detection tells us when we are moving, what is the direction we are following, and the step length enables us to know how far we are moving in a single step, though this could be replaced with a fixed length because human steps generally tend to be of fixed sizes. Let's see how we actually count the steps. For this, we use accelerometer data. As you can see from the raw acceleration here, that the accelerometer data is quite noisy. So we need to pass it through a low pass filter at a cutoff frequency of 6 hertz, because generally a human being doesn't move more than 3 or 4 steps in a second. And then we find the peak of the data, which corresponds to the point when our foot hits the floor. That gives us when we're actually taking the steps. The second part is walking direction. For this, we are using the gyroscope data. This utilizes the fact that human leg follows a reverse pendulum motion. As you can see from this picture, that the mobile phone goes up and down. So this axis, the rotation axis, is perpendicular to the direction of the motion. So the way we calculate is we get the gyroscope vector, we calculate the angle of rotation, then we rotate the local angle of axis to a global axis, and then we finally compute for every small time step. For every 10 milliseconds of data, we compute for the whole step and get the whole complete rotation matrix, and then get the rotation axis, and then rotate it by 90 degrees in order to identify the walking direction. So what are the considerations? So the considerations we need to have is the left leg and the right leg creates a different sort of motion. So we need to switch the angle to plus 90 degree or minus 90 degree at every alternate movements. And the data can also get properly polluted, and we can sometimes see that in two consecutive motions the direction changes by obtuse angles, which is not possible. So we need to ignore those. And third is the step length, which we use as a fixed value here. And the results, as we see here, that from the implementation, for very sharp turns, my method really doesn't work well, but for smoother turns, it can give results. For example, in 90 degrees, the orientation, like 90 degree or minus 90 degree, is an issue. As we have mentioned, as you mentioned, the sharp turns are an issue. So the possible mitigation strategies are: I try to remove higher if there are many high degree turns within 5 steps. I try to remove it with a single turn, and if there are many end turns with greater than 90 degree, we try to skip it. But these outcomes didn't really result in a proper in a didn't really result in better outputs.